Welcome to my talk, Interpretable Nearest Neighbor Queries for Tree-Structured Data and Vector Databases of Graph Neural Network Embeddings. Lots to unpack there. We'll dive right in. Querying data used to be simple. We had these nice relational databases and we had these table views. And when we had to look up, for instance, an author, we would just run a query and get the result. And it was nice to interpret because we could just see where our query matched the data. And even for text, we could do like similarity search on text and see which words would actually match and highlight those, and everything was nice and interpretable. Nowadays, data comes in all sorts of varieties as images, video, audio, graphs, and we want to do essentially the same, like look up data in our databases. So what we do is we take neural networks and map our multimedia data into vector spaces. And in these vector spaces, we can then look up by computing the nearest neighbors of our queries. As for instance, in this image on the left, we have a bunch of images and they are kind of grouped together by their similarity. And if we want to do a nearest neighbor lookup, we can look in the neighborhoods of the images. So queries become similarity search. In our study, the data we're interested in are mathematical expressions that we have crawled on archive.org. The approach is the same. We have a bunch of data points, then we embed them into a vector space with our neural network architecture, and then we can build an index of those embeddings and do a lookup for related or similar mathematical expressions. The problem is we don't really understand how the network computes these similarity scores. So this is kind of the usual problem with neural networks. They are always seen as kind of a black box that magically outputs some value. So we want to shed some light on what's actually going on inside of the neural network. Our data is equations. So what are equations? We view them as tree-structured data. Take a look at the example on the left. We have this empirical risk function, the sum over L. And what we do is we take this equation as LaTeX source and we compile it to an XML format named MathML, which was developed for the semantic web a while back, but it's still around. As you know, XML is essentially trees, and we go one step further and drop the XML markup and just view it as a tree where each node has features. So each node has features. In our case, those are binary because we one-hot encode the XML data, and then we get rather large vectors with lots of zeros and some ones as indicated by the green bars in this schematic. How does a graph neural network work? A graph neural network is kind of like a convolutional network, but for graphs. So what it does is it takes the feature vectors of a tree and transforms it based on local neighborhoods. So for instance, if we want to transform the root node in this tree, we take all its neighbors and compute a linear transformation by the matrix W. And then we take this vector that we get and we pipe it through an activation function sigma, for instance, the ReLU activation. And then we end up with a new feature vector that might have a different dimensionality. In this case, we have double the dimensions in the input. And we do that for all the nodes. And this is one layer of a graph neural network, and then we concatenate a bunch of those and we get a deep graph convolutional neural network. And I told you that we need a vectorial embedding. So what we do is we take all the nodes in the tree and we average them, and then we get one vector of a fixed dimensionality that we can put into our database. All right, so now we can compute similarities with those embeddings. And when we want to visualize the output of a traditional convolutional neural networks, what we do is we compute those saliency maps. They are supposed to highlight the regions where the neural network bases its decision on. Like, for instance, if we want to classify the horse, it's kind of important that we use the pixels that show the horse and not the green or the sky, or I don't know. So we want to do the same for our trees. And we propose two different approaches to do that. One is to compute a visualization based on the forward pass, and one is on the backward pass. All right. The similarity is defined as the dot product of two embeddings. So we have those averaged node features phi bar, and we just compute the dot product to get a similarity. And if we wiggle the math a bit, we see that the similarity can be decomposed as a sum over the nodes in our data of a dot product with the feature at the ith node times the query vector x prime. So we see that each summand has a different importance for the overall similarity, and we can thus color our tree according to this importance. So we say the color of the ith node is proportional to the dot product of the feature vector at the ith node and the query vector. This only uses information at the last layer of the deep neural network. And because we compute features as an aggregate over neighborhoods, over the layers, the information becomes less local and more global. So that means that we might have information on the last layer associated with a node that originates somewhere entirely different in the tree. So that might be suboptimal, and which is why we propose the backward-based approach. For the backward-based approach, we view the similarity and say, okay, how would this similarity change if we change the input? And we can gain insights into that by looking into the first-order Taylor approximation, which gives us the behavior of a function under small permutations. And this is based on the gradient of the similarity. So the similarity at x plus delta can be derived by the similarity at x plus delta times the gradient of the similarity evaluated at x. All right, so how do we get those gradients? Good news is that all neural network frameworks like TensorFlow or PyTorch are essentially just doing gradient computations. So they excel at that, and we can just use that. So now we can use our nice frameworks to get the gradient, and then we can color each node in our tree according to the gradient information. Unfortunately, the gradient is multidimensional. It has the same dimensionality as our input data, so that might be like 200 or more. So we need to have an aggregation to get to one single value. And we propose to just use the maximum, as it's usually also done for these conventional CNNs. Because we have one hot encoded data, we further modify this and only inspect the dimensions where there's a 1, and we just use the maximum of those ones in our input data. There's some things to say about MathML at this point, because the good news is that MathML is a markup language for rendering, so we can just tweak our XML and add the color information in. So we don't need to write a renderer for trees, we can just use the MathML itself. There's one problem with this approach, and that's that we can only color leaf nodes and not internal nodes. Leaf nodes in MathML are essentially all the letters, numbers, operators that you might have in an equation. And internal nodes are just for formatting, like putting stuff above or below a fraction bar. And those nodes are invisible. They don't render any characters so that we cannot color them. But we make do with just the leaf nodes. It's actually the majority of nodes are leaf nodes in MathML. All right, I want to show you some results. We always query the equation on the left, and then we show you the nearest neighbor in the data, visualized by the forward and by the backward method. So we start with the empirical risk function, and we see that the result is also an empirical risk. And both the forward and the backward highlight the important parts, that it's about a function over examples indexed by I, and the loss is important. What I like about the backward function is that it also highlights the hat over the capital L that's usually used for empirical risks or empirical estimates. So this is really nice. Second, I want to show you the empirical Rademacher complexity on the left, which we also find in the nearest neighbor. The highlighted functions are again almost identical, which means that there's not so much mixing in the neural network model. However, I like that the backward function puts a bit more emphasis on the supremum, which is kind of the essential part of the equation, because otherwise it would be just an expectation that would always evaluate to 0. So this is also nice. All right, there's more examples in the paper, and let me just finish with a quick outlook. The world is full of graph or tree structured data like social networks, molecules, electrical circuits, software dependencies. So math is really just one example. There's lots of applications to explore. And I want to leave you with this. Our artificial intelligence systems are often accompanied by visions of out of control AI that's generating these dystopian societies. So it's really important that we investigate as a community these systems and come up with guarantees and theories. And it's also really important that we educate the public about AI and its limitations as well. Thanks.